Hello and welcome again to my physics online video lecture series. In today's video, I want to discuss the parallel plate capacitor. I'm discussing this specific capacitor setup because it's a very simple setup, but it's also in some ways a very fundamental setup for capacitors and for understanding how capacitors behave. In fact, we can use what we're discussing today with parallel plate capacitors to make predictions about how capacitors should behave as circuit elements in a way that is more straightforward than using some more complicated geometries. It's also nice because a parallel plate capacitor, we expect there to be a more or less uniform electric field between the two plates, and that makes determining the capacitance a bit easier. So let's dive into this a little bit. We can begin with a little bit of exploration in the Colorado PhET simulations, specifically this Capacitor Lab Basics simulation. However, this simulation, for anybody who's taking a course from me online especially, is something that you really should do before this video. And even if you're just following along to learn as a pre-lecture for your brick and mortar, like in-person lecture class, or if you are not even one of my students, but following along looking for help in how to understand parallel plate capacitors, you really should tinker with this simulation before watching this video. Before we get to that, it might be worth recalling just what it is that we're doing with capacitors. So what is a capacitor, and what is its sort of defining feature? So a capacitor is basically a device which stores charges. The typical way that we think of a capacitor is that there's maybe two conductors involved, one storing a charge plus Q, one storing a charge minus Q. As it turns out, that need not actually be the case. A single sphere can act as a capacitor and has a capacitance associated with it, and yet it may be only storing charge plus Q without there being anywhere in particular that the minus Q has been stored. I suppose if you want to get more meta, then there is a minus Q being stored at ground or something like that. But for our purposes here, a capacitor is a device which stores charge, and we generally will assume that there's a positive charge on one conducting element and a negative charge on some other conducting element, which are separated in space. The thing to sort of recall is that capacitance is how much charge is stored per unit voltage drop. So basically you're looking at Q over delta V. Note that we assumed again plus and minus Q. This, if you want to be really technical about it, capacitance is a positive value. And so we're looking at just how much charge is being stored on, let's say, the positive charged device or conductor within the capacitor. And so it's Q over delta V with units of farad, where the farad is defined as coulombs stored per volt. So with that little background, let's go to our PhET simulation and kind of tinker around with it a little bit. We have two plates here, and we can put a battery between them. We can show the electric field, maybe. The electric field points from the positive plate to the negative plate. And we can do things like, having charged it up, maybe we'll take the battery away, and we can sort of like move the two plates farther apart or move them closer together. You see the little green bar graph at the top is telling us what the capacitance is in picofarads. And we see that the closer together they get, the larger this capacitance ends up getting. And this simulation also allows us to change the plate area, so we can make it smaller and then we get a lower capacitance. We can make it larger and we get a larger capacitance. Now what you should do before continuing this video, and you should do this whether you're taking this as a lab or whether you're not, just as an exploration on your own, is you should systematically go through and you should basically measure the capacitance as a function of the separation distance and as a function of the plate area. And you might do this both with the battery included and without it included, and you can look at other stuff like charge on the plate, stored energy, etc. You'll notice that the charge on the plates doesn't change as I move these nearer or farther, and it also doesn't really change if I make them larger or smaller. The capacitance and the stored energy do, however, change. And if I close the battery, I end up getting kind of a different result for things like stored charge and stored energy as I move things closer and farther apart. I can get quite a large value for these. And you'll find that the capacitance maybe doesn't depend on the battery itself, and that also means that the capacitance in this system doesn't actually depend upon delta V. Delta V is included in the capacitance, but it doesn't depend on the capacitance. So please do go play with that simulation on your own before continuing this video, because it's more fun to kind of discover things for yourself by kind of doing the experiment, even if it's a simulated experiment, than just having me tell you the answers. And the rest of this video, I'm kind of going to be telling you answers, and so that may spoil the experiment for you. So please go do the experiment yourself. Make a graph of capacitance versus distance between the plates, and of capacitance versus area of the plates. Try to synthesize these two graphs into one coherent relationship, and then come back and watch the rest of this video. So to understand how the capacitance is affected by these things like plate distance and plate area, we go to our equation again. C is Q over delta V, and then we consider for a pair of parallel plates like this, if I have plus Q here and I have minus Q here, then I'm going to have some electric field between the two plates. And of course this is shown in that simulation, that it points from the plus to the minus, which is what we would kind of expect from our basic understanding of what an electric field is and does. We actually know from Gauss's law what the E field is, and therefore we know what the sort of voltage drop is going to be. So let's label this. We'll say that there's distance d between the two plates, and then we'll say that each of these two plates has a sort of like a plate area given as A. Alright, from Gauss's law we can actually get the electric field value. Basically we're going to treat each plate as having a very large area compared to this distance d squared. So A is many, many times bigger than d squared. Basically this is near infinite area, or we can treat the plates as if they are infinite planes of charge. So Gauss's law for the infinite plane of charge is something else that you might recall from my previous video. Specifically, E is equal to sigma over 2 epsilon naught for each sort of plane of charge. Superposition means we can double that in between the plates anyway, and then 0 anywhere else for the E field. And so what that basically means is that our value for E in between the two plates is given by sigma over epsilon naught, and then outside it's given by 0. Now what that lets us do is a few things. First of all, we said that charge density is given by sigma. So parenthetically to all this, we note that sigma is actually Q divided by area, because it's how much charge per unit area. We've got charge Q on each of these plates. We've got area A for each of these plates. So sigma is actually Q over A. The second thing that we might recall from a previous video is what happens if you have a uniform field. And of course, this is basically a uniform field. And in a uniform field, basically, if you want to find the voltage drop between 2 points, measure the electric field from in that region and measure the distance between the 2 points, and basically take the dot product between those two things. And so what you end up getting is essentially E sub x delta x, which in our context means that delta V between the two plates is given just the E field that we have times the distance. And so what that means is that we can use the result we had over here for our E field strength, sigma over epsilon naught. So sigma over epsilon naught times distance, or in other words, Q times D over epsilon naught times A. Now we come back to our definition for C being Q over delta V. C is Q over delta V. We now plug this in for our delta V, and what we have now is Q divided by QD over epsilon naught A, which gives us a capacitance for the paraparallel plates of epsilon naught A over D, where again epsilon naught is the permittivity of free space. This makes sense now of the units for epsilon naught. The commonly used unit is farad per meter. Recall that epsilon naught is related to Coulomb's constant, and that the Coulomb's constant is 1 over 4 pi epsilon naught. And so that means that since Coulomb's constant has units of Newton meters squared per Coulomb squared, that epsilon naught could have units of Coulomb squared per Newton meter squared. As you can see, farad per meter is a much easier unit to use. Let's finish with a quick example. Let's determine the capacitance of a pair of parallel plates. The separation distance 2 millimeters, that would be D, and plate area 400 millimeters squared. We need to convert both of those into meters and meters squared respectively. Reminder that a meter squared, for each millimeter, you have a factor of 10 to the 3. When you have millimeters squared, that becomes a factor of 10 to the 6 difference. Thus, C is epsilon naught A over D, that is 8.854 times 10 to the minus 12 farad per meter, times 4 times 10 to the minus 4 meters squared, divided by 2 times 10 to the minus 3 meters, all of which works out 1.77 times 10 to the minus 12 farads. Or if we want to kind of round it to two significant figures and maybe use unit prefixes, remember that pico is 10 to the minus 12, so this is about 1.8 times 10 to the minus 12 farad, or in other words 1.8 picofarads. So that is our expected capacitance. And for comparison's sake, if you go back to that same PhET simulation, separation distance 2 millimeters, plate area 400 millimeters squared, our capacitance here is 1.77 picofarads. They've kept one extra digit of precision beyond what I rounded my answer to, so 1.77 picofarads is our answer. So hopefully this short video and this example have been helpful to you, and as always, thanks for watching and farewell.